Now let's try to do the following example. First of all, I go to the DVD, self, examples, malware, and I will use the Visual Studio version now, and it will be the patching and 04. In this example, we are going to use a very nice application which can speed off the finding of the position very much. It can be downloaded from the www.rohitab.com, and it is called as API Monitor. It's a very nice application. It has a portable version as well. I will use that one. So this is the portable version. I just copy paste it here, save it, and that's all. First of all, let's check how this application works. I enter to this directory, open a command prompt, cd to this directory, patching 04.exe, and you have to type some number. It works on the same way like the earlier one. And I print here, for example, 7, and it's plus. If I write here -7, then it's minus. If I type the 0, it's plus again. It's interesting, but anyhow, let it be plus. And now let's try to solve the problem again. We go to the API monitor, and it's a 32-bit Windows, so I will use the x86 version of it. Opens. Okay. Take a while while loads all the XML files. Those are loaded. And first of all, I have to mark what do I want to monitor. For example, I want to monitor the usage of the printf instruction. So I search for the printf instruction. Oops, it's not that one. Next. Not that one. Not that one. Okay. Forward only. It's here. So here is the printf, and it can be found at the ms vcr xx.dll stream. Oops. And within that, input and output, and Visual C++ runtime library. So I can just select any function, for example, in this case, the printf instruction, and hopefully I will monitor when does this instruction is called, and what was the input parameter to this instruction, and what was the output of this instruction, from what position it was called, and information like that one. I just open a command prompt. The process monitor immediately asks if I want to monitor the cmd.exe. No, I don't want to monitor it. And I go to the patching 04/release directory, and here is the patching 04.exe. Execute. The process monitor asks if I want to monitor it. The patching 04.exe. Yes, I want to monitor it. That's why I do. And I type here a number, for example 5, and it prints plus. What happened? I can see the printf instruction were called 3 times. First it print this text, then it was printing that text, and after that it was printing the plus text. Of course, we need this last one. If you come here, not here. If you come here, so whenever you select the call, then you will see here the address and the offset. So it will show you what is the return address after this call instruction. So if I go to the last one, the plus, the return address of this call was the 1046 position relative offset. At this time, the 00D4 1046. So here is the 1046. So practically I know the offset after the call of the printf, the application returns to this address. So just somewhere before this instruction, there should be that conditional jump, what we were always looking for. So we have the relative offset, 1046, great, nothing else we need. Oops, I don't want to monitor it. 0x1046. I just type it to a notepad because I don't want to forget. Now we can close the API monitor. We don't need it anymore. You can save the capture if you want, but now I just discard it. I don't need the window. And first I start the OllyDbg 201. Open it. File. Open. And open this patching 03 application. Release. Patching 04 application. Great, it's here. And now let's go to the position. Now the application will load it to the 00D4 base address. If you don't believe me, just press the M button. Here is the memory map, and you can see that the patching 04 is loaded to the 00D4 0000 base address. So we have the base address. So go to the expression 00D4, and we have here the relative offset 1046. 1046. Great. Follow expression. And really, there was some call ESI instruction before it, and after that call, it was the return address, so most probably this is the call printf. The ESI should contain the address of the printf when we arrive to this position. And somewhere before this call, there should be the conditional jump and the comparison. We can find it here. We can see here the text plus, text minus, and just before that there is the conditional jump. So again, we were able to identify the position, where is the decision, if it is a positive or negative number. And again, we found at the 10-2A position there is a jump greater or equal instruction. Again, the opposite of the jump greater or equal instruction is the jump not greater or equal, or it's simpler to use the jump less mnemonic. So we can just come here, right click, and overwrite this instruction to a jump less. Assemble, modified. Let's try if it is working. Run. Type a number, for example 5, and really prints minus instead of the plus. So this is how we can use it. Now let's try to do the same stuff in the other versions of Olly. I go to the version 1.1, OllyDbg, file, open, and now I open the patching 04, release patching 04, here it is, and go to the expression. Now it is loaded to the base address, 00D4 again, so 00D4, and add to it 1046. 1046, I arrive to this position. Before it there is a call ESI instruction, and somewhere before this call ESI instruction, sorry, I just make it a bit bigger. Here is the plus text, the minus text, and here is the conditional jump. So you just have to start to search for this position upward and try to find the conditional jump, what we need. If the application is more difficult, you have many conditional jumps and you are not able to decide, just put a breakpoint to all of them, start to run the application, and try to figure out which one is the one what you need. Again, if we just right click on it and use the assemble command, and instead of the jump greater or equal, we can use the jump less, assemble, run it, type a number, for example 5, and really prints minus instead of the plus. Debug restart the application, and now let's try to write a script to do the same thing. I go to the directory of the application, patching 04 release, and create here a new text document. I will call it as p4.txt and open it with Notepad++. And let's try to write the script. First of all, the script will look like as follows. I close the previous one. We have to find the base address of the application patching 04, but because it examines only 4 characters, it's enough, comma, and we want to get the module base address. The result is stored in the $result pseudo variable, so we just save the result to a variable. We are going to call it as other, and we save here the $result variable. We log the content of this other variable, add to this other variable the relative offset. And what is the relative offset? Oh, I forgot to show you in the previous round, but if I scroll up a bit, it's here. So the relative offset of it is 10(2e). So I just change it 10(2e). Again, we log this result just to see if there is some error. After that, move to this position, so we use the square bracket around the address because we don't want to override the variable, but we want to write to the position shown by this variable the value 7c. But if you were done in this way, then the Olly will understand it as 0000007c. No, we want to overwrite only 1 byte. That's why you have to add hash marks around it. So this is the simple script. What will do the patching, hopefully. And now let's try to use it. Go to the plugins, OllyDBG script and script window, load script, open p4.txt, and here is the script. You can use the right-click step command or the tab button to run the script step by step. And as we can see, the jump greater or equal is really changed to jump less. Oh, one more thing. If I click on the L button, that's the log window, or view log, then you will see here the true log result. Those are the 2 lines. Oops, those 2 lines. Great. So it is overwritten. Let's try if it is working. We just press the run button, type a number, 5, and really it works on the opposite way. Now let's do the same stuff with the next debugger, that's the Immunity Debugger. So I close the Olly and start the Immunity Debugger. File, open, and we open the C, patching 04, release, patching 04.exe, and let's go to the expression 00d4, and we know the relative offset 1046. So add to the base address. If somebody doesn't believe them, one can check it, really 00 there, so 1046. And we arrive to this position. I just scroll up a bit, and somewhere before this instruction there must be the conditional jump and the comparison instruction. Really, here is the comparison and the conditional jump instruction. So most probably this is the jump what we should modify. Instead of the jump greater or equal, as usually, we have to modify it. So assemble to a jumpless instruction. GL. Assemble, modified, run, and let's try if it is working. Write F5 and really prints minus instead of plus. Now let's try to do it automatically. So I restart the application, go to the same expression, and here you can read, where you can find the jump greater or equal is at the position 10 to E. So the relative offset of it is 10 to E. Let's go to the C, program files, Immunity ENC, Immunity Debugger, PI commands, and create here a text file. Let's call it p4.py. Use the Notepad++, and let's try to write the script. It should be the following. First of all, we import the Immunity library. It contains the stuff required for the debugging. Then import the struct library. It contains the little endian, big endian conversion routines. Then we create the main arguments. It is a mandatory if you want to script the Immunity Debugger, and it will get some arguments. Oops, I forgot the column from the end. Great. Then we create a debugger object, im equals imlib.debugger, opening and closing brackets. Then we want to get the module address. To it we will use the im object and use the get module function of it. And you should give the name of the executable patching 04.exe. That's the name of it. Great. And after that, we want to get the base address of this module. I will store it in the bybase variable, and I can get it on the following way: mod.get base address, and opening and closing bracket. We have the base address. Let's write it to the log, immunity.log, and I will log something like base address column 0x, because it will be some hexa value, and percentage 08x. I print it on 8 characters and hexadecimal, and I want to print the my base variable. Then we want to calculate the patch address. Patch address. It will be the base address, so my base plus 0x10.2e. This is the patch address, and like earlier, we want to print it. Patch address, and we want to print the patch address. Fine, it's printed. Now we want to save the original instruction. It will be only to show it. Original instruction is struct dot unpack. We know that because it is a short jump, it should be 2 byte long, and it is stored in this format, and we want to use the immunity read memory function, and we want to read from the position patch address, and from that position we want to read 2 bytes, and we need this result. And after that we save it again. Immunity.log original bytes and print here. It will be hexadecimal and 8 byte long. Of course, I can change it to 4 as well. Sorry, 8 character long to 4 character. That will be a bit nicer. This original instruction. And we want to create the patch. What going to be immunity.assemble. We ask the assembler to calculate how does the 7C looks like, and simple data, because we know that this is the machine code already. And write it back. Write memory to the patch address. The value of this patch. And return with some wizard string, for example, the OK. Save it. We have the script, and hopefully it's going to work. So, yes, is it restarted? Yes, it's restarted. So we have here the instruction. We just use the exclamation mark P4 command. Oops, and I made some mistake. I have to check it. Where was it? Original bytes. Okay. Original. I left here the percentage sign. Execute. And let's try it again. Great, now it was working. So change to jumpless. Again, if I press the L button to show you the log window, here is the result of the log, the previous case. So again, and after that it returns with an OK, or you can use the view log command, it's exactly the same. So we have the jump changed. Now let's run the application. Type here some number 5 and really it prints minus instead of the plus. And now let's try to do the same with Windows Debugger. I close the Immunity Debugger and this one as well. And let's start the Windows Debugger. It's debugging tools and WinDbg. So here, first of all, we have to go to the file, open workspace in file. And if you go to the themes, I use the standard VS view, but of course you can try many of them and choose your favorite one. Yes. And we have this interface. Now open the executable and go to the C patching 04 release patching 04.exe. Open, the application is opened. Again, what do we want to do? First of all, we want to read where is the base address. It's here. So the base address now is the 00D40000. So we want to go to the position 00D41046. But it doesn't go there. Why? Because as you remember, the Windows Debugger stops not at the application entry point, but stops when the Windows loader starts to load the application practically. So that's why we have to allow the application to load, because until that we don't see the data of it. And after that we will be able to see what is the information at this position. Of course, it has some advantage why it works on this way. It works on this way because there are some tricks. For example, the thread local storage. By the help of that, if the debugger stops only at the application entry point, then some code already run. So it's so a virus or some malicious code is able to infect your computer, even if you run it in debugger. So that's why it stops there. We are able to set the same behavior in case of Immunity Debugger or in case of the OllyDBG as well. You can use the system breakpoint, or in the newer version, it's even better. If you go to the 2.01 version of the Olly and select the options and start, you are able to stop at the TLS callback if defined, or system breakpoint. The WinDbg stop here. Okay, so we know why we cannot see the instruction. Now we have to find where is the entry point of the application. To get it, we can use the exclamation mark DH command and give it the base address. That's now 00D40000. And it prints the data here. I start to scroll back and search for the optional header information. Optional header. Yes, it's here. Here is the optional header. The optional header in reality is definitely not optional. It must be there. And I should search for the entry point. Where is it? Sorry, I was scrolled too much. Here is address of entry point 12FF. I don't know why I didn't see it, but this is the address of the entry point. So the offset of it 12FF. So the entry point will be at 00D4 12FF position. Let's put the breakpoint BP 00D4 12FF. I want to put the breakpoint. Great. Hopefully there is a breakpoint. Now I have to run the application until the breakpoint. Go. And the application stopped at my breakpoint. Now the application is loaded and I'm at the first instruction, this security init cookie. If you take a look, I forgot to emphasize it in the Immunity Debugger, or the Olly version 2 showed me the same data. And now if you just rewrite this address, now I am able to see it. Great. I have this instruction here. If I start to go upward, then hopefully I will find again the comparison and the jump greater or equal instruction at the position D4 10 2E. So the 10 2E is the offset again, obviously. Now we have to modify this instruction to change the jump greater or equal instruction to the jump less instruction. How to do it? We can use the edit instruction, and we want to edit only one byte, so AB. And we want to overwrite the value at the position 00D4 10 2E to the new value, what is 7C. And enter. And hopefully, if I go there to sorry, it's a bit upper. It's really changed to jump less instruction. Great. We modified the instruction. Let's try if it is working. Just press the G button. It's running. Come here, type a number, for example 5. And really it prints minus instead of the plus, so it works as expected. Now let's try to do the same stuff, but now automatically. To do it, first of all, debug and restart the application. The application is reloaded, it stopped again at the system breakpoint in the ntdll.dll. Again, we have to find what is the base address. The application printed us the base address, it's here, but now we want to write a script, and unfortunately the script is not able to read from the screen. That's why we have to use some kind of instruction to get it. The instruction is the !LMI, and we want to list the information about the patching 04.exe. And this LMI instruction gives us many information. One of them is the base address. It's here. Very good. We have the base address, but not only the base address, but also much more information. We have to somehow find the base address in this lot of information. How to do it? In case of Linux, it's simple. You just use a grep instruction to grep to this base address text, and you will get only that line. Something similar should be done in case of Windows as well. We will use the previous command, and there is a system command called find to find some text. For example, we are going to search for the text base address, but this find is a system command, so we have to explain somehow this Windows debugger. We want to use a system command, so the beginning of it will be .shell. This is the instruction, and we have to give it some switches. -i. We want to redirect to the find command the standard output of our command, and which command? The CI and this command. So practically we want to run this command, that's the CI, and redirect the output of it to the standard output, and because of that the find will be able to find the required information in it. Let's run it, and really we got only one line, base address, and something like that one. Okay, now we have the required information, but it is still too much. We need only the value 00d40000, and we want to neglect this base address, whatever stuff before it. Okay, how to do it? I will start to write some scripts, because now it is easier. In one line it was a bit too long. So I just go to the C root directory and I start to create the script. I created here because I don't want to type too much, too long pass. I will call it as p4.txt. Oops. I will open it with Notepad++, maybe I see it better with that one. And the previous instruction was this instruction. It's very nice. We should use this one. It's perfect. But it gave us the result, base address, column 00d4 and a lot of zeros. We are able to use the for-each command, .for-each. It can iterate through some text, and it is able to break them at the white spaces. So for example, now it will give you the base, then the address column, then the 00d40000. It's fine for us. And we need only this 00d400, so we have to skip, so /p, small p, capital S, the first two columns, and after that we don't need any more information, but unfortunately the for each expect us to give some iteration. So after it we want to get small p, small s every 10th column. There is of course no 10 columns, as you can see, the previous one, the last one. I just give some huge number what definitely will never exist. This is what I wanted to do. And in bracket, it's a for each cycle. So the actual object should be stored in some variable. I will call this object as OBE. So the actual object will be called as OBE. And what do I want to run? I want to run this command, or to be more exactly, this for each will store the actual element from this array in the OBE variable. And I just close the bracket. And first, do nothing else, just use the printf command, the value of this OBE variable. And this is our first script. Save it, and let's try to run. You can run it on the following interesting way. You use the $, greater than sign, less than sign, and give the path of the script C directory p4.txt. Execute, and really it gave us the base address. Finally we got the base address. Now the task is simple. We just have to add to this base address some value. To this we use the R command, that's the register setting or modification, and we will store in the $T1 pseudo register the content of this curly brackets object variable. So we store the value of this object variable in the T1 pseudo register. And let us add to this P1 pseudo register some value. For example, so I will store the result again on the T1 pseudo register. And what do I want to store there? I want to store there the $T1 pseudo register, the value of it, and I want to add to it 0x102e. Great, and semicolon. And now I have the address where I want to patch. And what do I want to do there? I want to do the edit byte, to modify 1 byte there, where at the position at $T1 there. And what do I want to write there? The 0x7c. This is what I want to write there. So this is how my script looks like in case of Windows Debugger. First of all, again, I put some breakpoint to the application entry point. That's the 00D412FF, as you remember, hopefully. Then I let the application run until the position is stopped at the application entry point. And then I go here, 2E, that's even better. I have now the jump greater or equal instruction at the 10-2E relative offset. Now let's try to run our script. This one. I hope I saved it. Yes, I saved it. And watch the jump greater or equal instruction. Enter, and it really modified to a jump less instruction. Great, we did the job. Just run again the go command to run it. And type here some number, 5. And now the application again works on the opposite way. So we were able to patch this application in WinDbg by the help of this small simple script.